Good morning, students. I'm Gnana Saravanan sir. So I'm handling you the subject called as electronic circuits one lab component. Even in this morning, I'm really glad to meet you all. So today we are going to do another experiment. So I will, as usual, I'll be explaining about how to do this experiment in the first step. Then I'll be moving on to the real hands-on kind of explanation or demonstration about the procedure to do the experiment. Right, let's move on. So today's experiment is experiment number 9 as per sequence. As per the syllabus, it is experiment number 5. So we have done all the bipolar junction transistor BJT's experiment, and then we are moving into MOSFET based experiment. So this is because you should have a continuity. So I just skipped fifth and sixth experiment, and we went on to all other experiments. So now we are in completing phase of the lab. So these two experiments which are left out is MOSFET based experiment. So we are shifting from bipolar junction transistor to field effect transistor. So in that also specifically MOSFET, metal oxide semiconductor field effect transistor, right? So today's experiment is going to be a common drain amplifier, or it is called as common means source follower. I think this kind of name follower, source follower should be familiar to you, because I think we have already seen another kind of amplifier similar to this. So that is common collector amplifier or emitter follower. So Anga, I think I have explained what is emitter follower. Similarly, today we are going to see what is source follower. So this experiment is more similar to that experiment. So keep that in mind. Or if you haven't watched that video, go back to YouTube, see the playlist. You select a source follower or common collector amplifier and see that and come. Right. So the agenda of this experiment. So this experiment is going to be a frequency response of source follower. So as such, like previous experiments, the agenda is pretty clear. So we need to measure the gain with respect to the frequency change. We'll try to tabulate it. We'll try to plot the frequency response, and we'll try to check whether there is a bandwidth that is available. So mostly this experiment and the emitter follower will not have a bandwidth, because they'll have a constant out means the output gain remains constant over the entire range, because whatever at the input is going to follow at the output. Another follower. Anyhow, so this is what you see here is the pin configuration of MOSFET. So we are using IRF Z44. So that's the MOSFET configuration, means that's how, and the name of it, right? So the symbol is shown here. It has 3 terminals, actually 4, but at the output you have only 3 terminals. So gate, source and drain, substrate and source are joined together. So the 4th terminal will be as substrate, so that is not necessary. So both are short circuited. So as far as the pin diagram is concerned, the first pin is gate, the second pin is drain, and the third pin is the source. So it's a plastic package, it's a flat package, SIP package, right? Single inline package. So it's called a SIP, right? So let's move on to the circuit diagram. So this is the common drain amplifier or the source follower. So here you can see this is gate, and this is source, and this is drain. So input is given to the gate terminal, and output is taken across the source terminal. So the only terminal that is left of the order that is common between input and the output is the drain. So that's why you call it as common drain amplifier. Here drain is common to input and the output through VDD, not through the ground. So the same similar case now I explained it in emitter follower also. So emitter was common between input and the output through VCC. Inge will call it as VDD. Why do we call it as VDD? Because it is the voltage is given to a drain. So its name, the designation is given as D, drain voltage, right? So these are the components values, and let's move on to the next slide. So procedure, right? So the procedure is pretty similar to the previous one. So connections are given as per the circuit diagram. So whatever be with the circuit diagram, you'll try to connect it. We need to set the input voltage to be a fixed constant value. So here we'll be trying to set 1.5 volt as the input voltage. We'll vary the input frequency and we'll note down the output voltage change. So we'll try to check whether there is an improvement in the gain. We'll tabulate the reading and we'll plot it on the semi log sheet and we'll try to find the 3 dB bandwidth. So that's it. Okay. So the graph, the output graph on the semi log sheet will be something similar to this, or it will be more over a straight line, right? So the graph is plotted between the frequency change and the gain on the other scale, y-axis. So this is the log frequencies on the x-axis, and the y-axis will be a normal scale. That's why it's called a semi-log sheet. So anyway, I'll explain that in a separate video. Tabulation, you see the input voltage is common, it's fixed value, so it is 1.5 volt, right? And we'll vary the frequency, we'll note on the output voltage, and the gain is being calculated. So I think that's all on the theory part. Now it's time for us to go and to see a live demo and to understand how it really works as expected. Yes, students, let's go and check out how this really works. So here is where we are. So this is the setup. So as usual, you can see that there is a function generator. It will generate some frequencies. And here you can see there's a RPS, so that is used to give VDT, and there is a CRO to view the output waveform, right? So in the input is given from this function generator, so you can generate square waveform, or let me show it to you. There are three buttons: square, triangular, and square, triangular, and sine waveform. So we have selected sine waveform. So almost I've kept 1.9 kilohertz. And you see the input voltage is around 1.5 voltage. So let's check the output voltage is seen here. So you'll vary this frequency and you'll note down the output. See, you'll vary this frequency and you'll try to note down the value. So right now I'm going to keep 1 kilohertz, like 1.014, 1 kilohertz I've selected. And if you see the output, you can see. So it is one box into 1 volt per division. So it is 1 volt. So input is 1.5 volt, and for 1 kilohertz, the output is 1 volt. So the output voltage actually has reduced. So that's why the gain has reduced. So you can see that this is the readings. So you can pause this video even and you can note it down. So I have started from 60 hertz and run to 3 megahertz. You can see that over a wide range, you see the gain remains constant around 1 volt. So that's, and the output gain is also, it's constant. So we have checked it for 1 kilohertz. For 1.5 volt input, we have got 1 kilohertz. So that's the output. So regarding construction, you can see that this is IRFZ 44. So here there is, see, here there is a biasing resistor, and there were 2 more resistors running from the source is being given. So the output is taken across the source, the third terminal, right? And the input is given across the first terminal, which is the gate, source, drain, gate, drain, source, GDS, G input is given, and drain directly it goes to VCC, and S you get it, the output. So this is construction. So this is how we need to do the experiment. So at the output, you can see that since the gain is constant, you'll simply get a straight line, and there's a small decrease at 2 megahertz and 3 megahertz. So gain will slightly decrease. So that's how we need to do this experiment. It's very simple. It's as like the previous experiment, right? Hope you understood. And the readings also, it's easy to do. So in a separate video, I'll explain you how to do or how to plot the semi-log sheet, right? So see you all on the next video or with the last experiment. Until then, it's bye from GSL. Take care.